So in chapter 2, we start looking at some definitions of atoms, molecules, and ions, and we begin by looking at the earliest ideas concerning the atomic theory. So a lot of this is review from Chemistry 139, but I think it's important to mention that you don't want to make any assumption about the level of difficulty of the work. So the theoretical material is very similar to what you saw in Chemistry 139. What you're going to be asked to do with that material is a little more complex. So in modern chemistry, we take an atomistic view of matter, and the atomistic view of matter was first explained by this guy Democritus around about 2,500 years ago. Well, it was first written down by him. Other people may have had that same idea. And these early theories were not supported by any physical evidence. They were just people sort of like hypothesizing in the philosophical sense. So in an atomistic view, we think of matter as being composed of particles that are called atoms, and these particles are indivisible by either physical or chemical methods. So what that means is that we have these different atoms, and they have different sizes and shapes, and they're kind of like building blocks. We can put them together in a whole variety of different ways to create all of the samples of matter that we see around us. And when we connect them in different ways, we get different kinds of matter. So that's the general kind of principle, that we have a set of building blocks and we're just going to kind of like reorganize how they're connected to one another in different ratios and in different styles and get all of the things that we see around us. So it wasn't until 1808 that this kind of general idea got, broadly accepted and was developed into what we would think of as being a modern scientific theory. And this was done by a guy called John Dalton, who was an English school teacher. Now, Dalton was an interesting guy. He had a lot of research interests, and he was also, you can see he was wearing glasses, he was also colorblind, and for that, he studied colorblindness, and for that reason, colorblindness is sometimes referred to as Daltonism. John Dalton was also interested in things like the weather and studied gases, which we had previously studied. Now, in John Dalton's atomic theory, there are 5 big ideas, and I've rewritten them here in sort of modern language. He wrote them in sort of the language of the 19th century. So these are not a direct quote, but it's my best attempt at interpreting them. The first thing that he said is that all matter is composed of tiny indivisible particles called atoms. So he's just reiterating the atomic theory of Democritus. And then he says atoms of one type are the same as each other and different from other types of atoms. So what he's really saying is that every carbon atom is the same as every other carbon atom. Every nitrogen atom is the same as every other nitrogen atom, but carbon atoms are different from nitrogen atoms. In fact, carbon atoms are different from every other type of atom. Same with nitrogen atoms. They are different, they are unique in comparison to every other type of atom. Now, again, this is kind of just an extension of what Democritus was attempting to say without evidence. Dalton says that the number and arrangement of atoms types in a pure substance determines identity. So we had 3 atoms before, and if I put them together with the round atom type in the middle, that's going to be a different substance than if, say, I put it together with the square atom in the middle, or if I mix up the numbers. Alright? So it's the number of atom types and how they're connected that determine the identity and the properties of a pure substance. Dalton then said that when a chemical change occurs, what's going to happen is that the atoms that are present will combine, separate, or rearrange how they are connected to one another. So earlier on, I spent a lot of time saying that chemical change always involves the making and breaking of chemical bonds. And this is Dalton reiterating that. And then finally, this is an interesting one, and because some of you talked about this topic in your discussion of the scientific method, he says alchemy is wrong. Quite strong words, because there were still some people that were on the fence regarding alchemy. He says that atoms cannot be created, destroyed, or transformed into other kinds of atoms in a chemical reaction. Why? Because when you have a chemical reaction, when you have a chemical change, all you're doing is reorganizing how your atoms are put together. So you might separate some atoms, for example. Okay? That's it. Or you might combine some atoms or reorganize how they're connected. But that's all what's happening. So atoms are not created, destroyed, or transformed in a chemical reaction. So what makes Dalton's theory different from what Democritus was saying was that he had physical evidence to back it up. He didn't just kind of like, propose an explanation with no evidence to back it up. Dalton used information regarding the masses of elements in different compounds to formulate his atomic theory. Now, it's a little bit complicated, but there were two laws that had been recognized by Dalton's time. The first one was the law of definite proportions. And what this says is that in a pure compound, the elements are always present in the same definite proportion by mass. So if you take a sample of water, you always get 2.02 grams of hydrogen for every 16 grams of oxygen in any sample of water, whether it's made in the lab, whether it's recovered from a river, whether it falls from the sky. That's how it is, which is kind of interesting. And every compound has its own characteristic ratio of the element parts by mass. So you can take two different samples of something like ammonia, break it down into the two types of atoms that are present there, nitrogen and hydrogen, and you can measure the relative proportions of those two types of atoms. So we've done it here for two different samples of ammonia. One has a mass slightly lower than the other. And what do you see when you go through and you calculate the total percentage of nitrogen atoms by mass and the total percentage of hydrogen atoms by mass? It is, within experimental error, exactly the same for both those samples of ammonia. And you could take any sample of ammonia, wouldn't matter the source, wouldn't matter the size, and if you figured out the percent nitrogen by mass and the percent hydrogen by mass, you would always get these numbers. Okay, so how did Dalton interpret this law of definite proportions? Well, he says that what it means is that a compound always has a fixed whole number ratio of the atom types present. So water always has 2 hydrogen atoms for every 1 oxygen atom. And if it doesn't have that ratio, it's not water. Salt, sea salt always has 1 sodium atom for every 1 chlorine atom. Always. So that's what's going on there, right? And every compound has this characteristic ratio of the masses of the atoms that are present. So there was another law that Dalton had to work with to help him formulate or to provide evidence for his modern atomic theory, and that was the law of multiple proportions, which is a little bit more complicated to understand. And what the law of multiple proportion essentially says is that when 2 elements react to form more than one compound, a fixed mass of one element will react with the masses of the other element in a ratio of small whole numbers. So if I have 2 elements, A and B, that react to form a compound, and and they form a series of compounds, one with say 1A and X lots of B, and then the other one with 1A and Y lots of B, right? If I have like 1 gram of A, I would have 5 grams of B. And then if I have a fixed mass, right, it says here a fixed mass of one element, 1 gram of A in this guy, I might have 10 grams of B in that one. And when I take the ratio of these two, right, 10 on 5, I get a simple whole number. And you see that again and again and again and again. Alright, so let's just have a look at an example. We've got 1 gram of copper reacts with 0.588 grams of chlorine and it makes a green compound. We take the fixed mass of copper, react it with a different mass of chlorine, and we get a different compound. And what this is really saying is that if I take the ratio of the masses of chlorine, I get a simple whole number. Alright, I get a simple whole number ratio. So that's, and he had a bunch of stuff to support this. Alright, so how he interpreted this is that as an atom of a given type has a fixed mass, then the atoms are combining in simple whole number ratios. So we might think of this as being in the first compound, copper is combining with 1 chlorine. In the second compound, copper is combining with 2 chlorines. Now, what we really know is that it's double the mass of the chlorine, so we can't necessarily be so specific here, and X is unknown, right? But they're combining in simple whole number ratios. So Dalton interpreted this as different compounds have different whole number ratios of the atom types. Water is different from hydrogen peroxide because they have a different ratio of atom types. Ammonia is different from hydrazine because even though they have the same atoms, they're in a different whole number ratio. Methane is different from propane. Again, they have the same atoms, but they're present in a different whole number ratio. So that sort of fleshes out the two big early theories describing how atoms behave and interact with one another. And largely Dalton's theory remains intact. There is a bit of a few comments that can be made. One of the ideas that Dalton had was that atoms were indivisible, can't be destroyed, and can't be transformed. Now, this is in a chemical process, and that remains correct, but it should be recognized that in nuclear reactions, these things become possible. But at the energies that we'll be looking at, the type of energy that's involved when you just mix two substances together in a chemical process, Dalton's theory still holds. The other thing that we'll recognize when we begin to talk about isotopes is that Dalton said that atoms of a particular type are identical to each other. So his other postulate was atoms of a given type are identical to each other. And this doesn't take into the account the possibility of what we now describe as isotopes of an element. So Dalton's theory has been modified to include the possibility of isotopes. We'll talk about that in a little while. Okay, hope that was helpful, and good luck with everything.